Let's remind ourselves what tangent is. Tangent, the tangent of an angle, in this case, tangent of A is the angle we're using in this graph, is equal to the opposite side of the triangle divided by the adjacent side. So, for example, here is we'll go like a normal angle like 30 degrees like we're used to. The opposite side here, we know that that is the sine of 30 degrees, which is 1/2. And the adjacent side, which is this, is the cosine of that 30 degrees, which is the square root of 3 divided by 2. Um, Tangent is equal to the opposite divided by the adjacent. So if the opposite is sine and the adjacent is cosine, like tangent of alpha, cosine of alpha, sine of alpha, cosine of alpha, that means that tangent of A, or alpha, is equal to the sine of alpha divided by the cosine of alpha. So, and this is what we're used to seeing. And what's interesting, there's a few interesting things here, right? As we change this value of A, you can see that that triangle changes. And I have listed what the value of cosine is and the value of sine is, and I just have that point labeled here. And we know, like for example, right at 60 degrees, we know that the tangent of 60 degrees is the square root of 3. And the reason that is because this point right here, 1/2 comma root 3 over 2, is the coordinate point that we get on the unit circle when we have a 60-degree angle. And so if we take that square root of 3 divided by 2 and we divide that all by 1/2, we just get the square root of 3. So you see the tangent here is the tangent, which I call B, is 1.732, and the square root of 3 is 1.732. So this makes total sense. Now, what's interesting about tangent, though, is that if we consider it being the y value divided by the x value, or the cosine value divided by the sine value, if there's ever a point where that, the sine value divided by cosine value, if there's ever a point where that cosine value is 0, then what we would have to be dividing by 0, right? Because look, this is the denominator. And so if cosine of alpha was ever 0, or cosine of A was ever 0, we'd have a problem with tangent. And we do. So cosine of 90 degrees, right here at this point, cosine will be 0. The x value will be 0. So if I change this to 90, tangent becomes undefined, which is because we're dividing by 0. Now, something you can also notice here is if I got really close to this, but not quite, like let's say 89.9, tangent, the value here is 572. Okay. If I made it even closer to 90 degrees, but not quite, it's 5,729, 57,295, 572,957. Or as you can see, as I get larger and larger and larger, or closer and closer and closer to 90 degrees, but not quite, the value of tangent gets higher and higher and higher. You can say that the tangent approaches the value of tangent as the angle approaches 90 degrees, the value of tangent approaches infinity. But it can't ever get to infinity, and so what we're going to end up having there is this domain restriction. We'll have a domain restriction to tangent whenever we have a cosine value, so it'll happen again at 270 degrees of undefined. Of 0. So also notice something else. If we define tangent as the sine of alpha divided by the cosine of alpha, and I have the cosine is the x value and the sine is the y value, well, isn't that just the slope? So tangent is like the slope of this green line here. And so anytime I'm dealing with an angle, either this angle here or this angle here, I'm going to have positive values for tangent because the slope of this line is positive. If I have it over here, now this looks like this line has a negative slope, so tangent values are going to be negative here. And so this is just this is what tangent is. It's sort of how it works. And so now let's look at the graph of tangent. So I have the value of tangent shown here, and I just did this. The way I set this Desmos graph up, I had to just kind of modify what A is, but don't worry about that. So as we adjust the angle here at 45 degrees, we know that tangent is going to be 1 because the sine of 45 degrees is square root of 2 over 2, and the cosine of 45 degrees is square root of 2 over 2. So you divide something by itself, you get 1. And then as we get closer and closer to 90 degrees, so pi over 2, that tangent value is going to start increasing very, very fast. In fact, it can't get to 90 degrees. Do we have this if we zoomed out really far, it would never actually get on this line, which we call, well, this whatever, wherever pi over 2 is on this line, we don't have it shown here, I guess right there. It wouldn't get there because there's a domain restriction, because we said that we'd be then dividing by an x value of 0. Cosine of theta or cosine of 90 degrees is 0. As soon as you drop back down after 90 degrees, like 91 degrees or 92 degrees, now we have really big negative values, and then we're getting closer up here. It's just like this, right? As I had this slope of this line is like really high, a really big positive value. This is undefined, and this is a really big negative value. The slope of this line is a big negative value. So if we go back here, it makes sense, and we have a big negative value, and then as we get closer and closer to that flat 180 degrees, right, the tangent of what is the slope of a horizontal line? It's 0, right? So we have this, and notice now too that the period, like we talked about for trig functions, the period of a trig function is when it starts to repeat itself. So if we said it started right here, and then it's going to start repeating itself right here. So that means that now we're not dealing with a period of 2 pi like we were for sine and cosine. We're dealing with a period of pi. And the fundamental period of tangent is pi. We can also see that on our other Desmos thing here, is that if I have either this angle right here or this angle right here, this tangent is the same. Okay, it's always going to be the same. The slope of the line here is the same on either this angle or this angle. Same deal for these ones, right? It's this angle and this angle, they're the same. And so we don't have it where we had sine, where it was repeating every time we went around the whole circle. And now every time we go around a half circle, it starts repeating itself, okay? So the period of tangent is pi. The fundamental period of tangent is pi, but the graphing is a little different. Notice something else. Okay, if we know these values, right? We know that the tangent of pi over 6 is the square root of 3 over 3. We know the tangent of pi over 4 is 1. Tangent of pi over 3 is the square root of 3. Those values will just keep repeating themselves. Like you can see, they keep repeating themselves. This is like what the standard tangent function kind of looks like here, and we still have this a. But when we talked about sine and cosine, we talked about the amplitude being the height of the curve, right? The height of the wave. But the like distance from the midline to the height. That's not a thing with tangent, right? The distance from the midline to the maximum height of the tangent curve is infinity, because it just keeps going up forever. So A now is not really called an amplitude, but it still does the same thing, is that in that it is a vertical stretch. So if I had a larger value of A there, I would have a graph similar to this blue graph on the right here. It would just be stretched vertically, so it would be kind of more, be like, I guess, taller is a way to think of it. Okay, so that's what tangent looks like. You could even draw in. We could even write in the the vertical asymptotes here. You can see that at this blue line will never touch that red line. We'll have another one at 3 pi over 2, because these are values where cosine pi over 2 and 3 pi over 2, those are angle values where the cosine of those angles is 0, where we have a domain restriction. So that is the graph of tangent. It's this strange looking thing. And the graph of cotangent, we've talked about cofunctions a little bit, is the exact same thing. It's just shifted over pi over 2. In fact, we could type in, I don't know if I can actually, maybe I can, the cotangent of x. There's some things to consider about that. But anyway, so yeah, that is the tangent of x, the tangent of theta. That's what the tangent function looks like. And we are going to look into graphing tangent now by hand, a couple different versions of the tangent function.